Hello, this is the next video in a playlist that I'm calling Hypothesis Testing. And here we're in part 6 of a little mini-series that I'm doing on two-sided, uniformly most powerful, unbiased test, simple versus composite hypotheses. And we're in the Poisson setting. So the null is that the lambda parameter is equal to some value lambda naught versus the alternative that lambda is not equal to that value. Now a must watch is a video, the video just before this one in the playlist on two-sided uniformly most powerful unbiased test in the Poisson setting. So let's just jump right in. I always like to remove all the objects from the list. Let's assume that we're testing lambda is equal to 2, and that's I put, and the L0 stands for lambda naught. Let's do it at the alpha 0.05 level, sample size of 25. What I do here is I create all reasonable combinations of C1 and C2. And C1 and C2 are the cutoff values in this test, the UMPU test. And so I create a matrix with all those, and since it creates all combinations, I only want the ones where the C1 is strictly less than C2, so I get rid of the other ones. And then a must watch is the background video, the video just before this in the playlist hypothesis testing, where we create constants K1, K2, K3, 4, 5, and 6. Now that goes by each row of the matrix. CR stands for critical region, because it's a matrix of possible C1 and C2 values. So we just mow through that. Then it creates two equations, two unknowns. So in the first equation, you solve for G1 in terms of G2, and you plug that into the second equation, then you solve for G2, which G2 is the gamma 2 in the test function. And so that's what this is. Then you take G2 and plug it back into the first equation and get gamma 1 or G1 in here. Now, since gamma 1 and gamma 2 are part of the test function, they have to be between 0 and 1. So we isolate all the gamma 1 and gamma 2s that are between 0 and 1 and remove all the others. Well, it turns out that is a unique solution to that. Now, before I show you what C1 and C2 are, I want to test for the alpha level. And so this is a function where it looks at the area, the height of the bars, area under the curve, for in the Poisson, using the cutoff values and the gamma 1 and gamma 2 values to see if it is 0.05. And it is a 0.05 test. The cutoff values are 37 and 65. Gamma 1 and gamma 2 are this. Note that it's almost 100%. If the test value lands on 65, we reject with probably 0.997. That's kind of interesting. So let's look at the power curve for this setting. And here it's really we change up the lambda values, and that's sorts of this x is where it's n times lambda. That's the Poisson distribution, but we put an x there and let it vary, and that's how you find the power curve. And then we plot it and draw a line at alpha 0.05, and that's what this is. So it's a simple versus composite hypothesis. So the simple, it's just one point at 2, and then everything else is in the alternative region. And notice that the power curve is always above this dotted line, which is 0.05, so it's unbiased, and it equals 0.05 at 2. So this is it. This is the uniformly most powerful unbiased test for this situation. Now let's do a computer simulation. So the cutoff values that are in the matrix, I go ahead and just put into a variable. In the gamma 1, gamma 2, we do 1 million loops. I generate 1 million random Poisson values within 1.25. Now remember, this test is developed when lambda is 2, so this is, it's clearly not 2. So let's see what the power is, the probability that we reject when we should. So we create those, and now this temp counts how many times we would have rejected or not for each of those 1 million replications. We table it, and we might as well divide that second one by the number of loops, which then gives us the simulated power. Let's go ahead and plot that in our power curve and look at it. So at 1.25, the simulated value was this, 83%, I think is what it said. And look how close it matches to the theoretical power curve. So that's a good sign. And that's it. Now for a second approach, and this is what I find pretty fascinating. Oh, and before I forget, I always copy and paste the code into the comment section so you can copy and paste it in R and then play around with it, at your leisure. So what we do is we want the left tail and the right tail to be alpha over 2. So that means it's an alpha level test. And so we use the Poisson, which is the cumulative distribution function for Poisson. We want it alpha over 2. We want the right tail alpha over 2. And then we solve for the gamma 1 and gamma 2 that makes the total area, or the probability, alpha over 2. And let's test to see if it is a 0.05 test. So this here looks at the probabilities of being in the rejection region, and it is 0.05, right? And so the new critical values for this equal tells approach is 37 and 64. And here, for the UMPU test, it's 37 and 65, so it's a little different. And that's it. And so let's create a power function for the equal tells approach. That's what this does. Now let's plot the two curves on top of each other. And this is what I find fascinating. Now they advertise the equal tells test as approximately unbiased, uniformly most powerful. And if you look at the two curves, now on my screen I can tell that there's a slight difference in these two curves. I'm not sure if it'll come across YouTube that way. But look, the test looks unbiased. It looks like both curves are above 0.05. And so we're going to zoom in 2 or 3 times very slowly. So let's zoom in a little bit. And you can see that the curves are different in this illustration. But it also still looks sort of unbiased, right? They both look above 0.05. So let's zoom in one more time and look at it. And now you can see that the curves are separating more. But remember, this difference, this vertical difference, is actually very small. And here you can sort of just barely tell that it goes below 0.05. So let's zoom in one more time and look at that. This is the last zoom we'll do, and you can tell that it does go below. And remember, it's a simple versus composite, and the composite is everything besides 2, so it dips below the 0.05 level in the alternative region, so it's not unbiased anymore, but it's approximately unbiased. And that's so small, but finding those rejection regions is so easy in the equal tell test that's actually what most people conduct, and not the UMPU test. Okay, well, that's all I have for this video. Hopefully you enjoyed that. I sure did. Please like the video and subscribe so you don't miss the next one. Thanks. Bye.